honor to have with us today Orit Raz here. Orit is a professor at the Hebrew University in Jerusalem, and she's spending the year at the Institute of Advanced Studies. So we managed to coerce her to come all the way to the city and tell us about her work.
Okay, hi. Thank you for inviting me. I'm happy to be here. So the title, you didn't say the title. So the title is a Hausdorff-dimension analogue of the Elekes and Rónyai theorem. And I'm saying it because let me start by introducing the theorem itself and then give some more background as I continue. So the Elekes and Rónyai theorem is a theorem. I'm going to talk about its Hausdorff-dimension analog, but the original theorem is in the discrete setting. So I want to introduce first of all the original settings, the discrete setting, the theorem. So the problem of the Elekes and so the problem is the following: you have a polynomial with two variables with real coefficients, and you're given two finite sets of real numbers. So A and B are finite, each of size n. And what we're interested in is the image set of A Cartesian product B under the set, under the function. So f of AB, the value is f of AB, where A is from A and B is from B. And so if each of these sets is of size n, we consider here n squared pairs. So we might expect that in general, the size of this set will be n squared, but maybe one can choose A and B in a very special way, such that there are many repetitions here, and maybe this image set can be smaller. And so indeed, if f is the function x plus y, I can take A and B to be an arithmetic progression, and then indeed we will have only an order of n distinct values. But for a general f, we don't expect this to happen, and this is indeed the theorem of Elekes and Rónyai from 2000. It says that if f, I'm trying to think how to, I want to somehow have the board split into the discrete setting and the Hausdorff-dimension setting. So I'll try to do that and see if it works. And so the theorem says that if we have a polynomial with two variables, then one of the following two alternatives holds. So either for no matter how you choose A and B, the image set will be large. So f of AB, okay, maybe all right. So either for every AB, we're going to cardinality n, the image is more than n. So Elekes and Rónyai showed little omega of n, but later it was improved several times, and currently the best exponent is of Shormushi and Zahl. So they show a constant times n to the 3s. This is the very recent work of Shormushi. And if so, this is one alternative, and otherwise, this means that f is essentially x plus y. So f or f is one of the forms. X plus y. So I want to write x plus y, but it can be q of x plus q of y. So this is 1 or h of px times q of h. Let p q of h are univariate for units. We don't receive such polynomials, and this is actually the same thing because it can compose h with a log. And let's these are the special forms. So either f is essentially x plus y, or the image must be large. Okay, so this is the discrete setting. What do I mean by the Hausdorff-dimension analog? So in this, so in the So what I want to do here is instead of taking finite sets, let's take infinite ones, and then instead of thinking about the cardinality of the sets, let's look at their Hausdorff-dimension. So a theorem, which is a joint work with Josh Zahl. So we proved that if f is a polynomial of variables, then one of the following holds. So either for every AB subsets of R Borel sets, dimension. So dimension is always Hausdorff-dimension. The dimension of A equals the dimension of B equals alpha. Then the dimension of the image set is at least alpha plus some constant, or really it's a constant, like a positive constant that depends on alpha, or f is one of the forms. Exactly as before. I denoted it by star. One of these two forms. Okay. So as you can see, it looks like exactly the same statement, only that instead of a cardinality, we now have Hausdorff-dimension. Right. So when you see these two statements, one can wonder: are they only these two statements? Are they only do they only look the same, or maybe they're really related? Can I use tools from this setting, from the proof of the theorem in this setting, and use them in the other setting? Or it's just coincidence that both of the statements are true. Okay. So this is not the only example of two such statements in the two settings that look like that. So I want to give some more examples. Okay, so I'm going to just a way to raise it. But...
Can I ask you a question before you?
Yes, raise it.
No, that's fine. I mean, how crucial is the assumption that it's a polynomial? Can you relax this?
So actually, yeah, so in the Hausdorff-dimension, we actually prove it to an analytic function. It's somehow easier because we restrict ourselves to a compact domain. For the discrete setting, I think that if you will restrict to some like to the square, then I think you can still do something. I can tell you more later.
Thank you.
Yes, you can say things about that. Okay, so other examples where you have this analogy. So, for example, maybe I should follow my notes. I think my notes will say the Erdős distinct distance. Okay, so Erdős distinct distance is problem. So probably you all know it, but let me just mention it briefly. So we have a subset of R2, a finite subset of size n, and we consider the set of distances that are spanned by this set P. So the distance between P and Q, where P and Q are constant. And as before, we have here P of size n, we have n squared pairs. In general, we expect to have n squared distinct distances, but maybe one can choose P in a very special way so that we have many replications. And indeed, Erdős showed that there is a choice for every n sufficiently large. There is a choice of P such that the number of distinct distances is much smaller than n squared. It is some constant times n over square root log of n. And he conjectured that this should be the best possible. So for any choice of P, we'll have at least this number of distinct distances. So Erdős conjectured the cardinality of P is at least a constant times n over square root of n. And this was the Gutenberg for this. Not this, but almost this. So they proved that the cardinality of P is at least constant, not the same constant, n over log n. So up to square root of log n. the improved conjecture. And so this is what I want to say here. And one can also, I want to mention because I will need attention, so one can also ask about the thin version. So maybe not only that the number of distinct distances is large, maybe there is one point of P that will be a witness that there are many distinct distances. So if we consider only maybe three versions too. So we consider the distinct distances from one specific point of Q. 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 So Q is fixed and go in very P. So maybe there exists one concept that this set is already masculine.
Is Q in the set?
I'm sorry, that's it. Yeah, I didn't format, but yes,
Could be. Depending on what you want, whatever you.
Yeah, I think
whatever you want.
probably if it's not, then probably it's easier, I'm not sure to find one, but for some. So the question here would be, does there exist Q in P such that this set is large? I really just wanted to put annotation because I will. Okay, so this is in the discrete setting, and I want it to look like a table. I'm again erasing this. Because otherwise, okay. So in the Hausdorff-dimension setting, so we have the problem of the Falconer. The Falconer. This is this one. And so in Falconer's problem, we have acted of R2, which is a Borel set, and so conjecture. What kind of conjecture that if E is a Borel set, that E Borel, the dimension of E, Hausdorff-dimension of E is at least one, then the Hausdorff-dimension of the set of distances spanned by E will have dimension also at least one. It's the set of distances is in R. So this is the conjecture, and we prove that this dimension must be at least 1/2. And in 2003, so again, that's some reduction of pattern tau. It's kind of what I'm trying to produce now. There is this reduction. So Bourgain proved using a reduction of pattern tau that he improved the 1/2 here of Falconer. The dimension of the distance that is at least 1/2 plus the constant for some absolute constancy. But again, as you can see, it looks like the same statement, only this is in the discrete setting, this is in the Hausdorff-dimension setting. And one of the example that I want to list here is the sum product problem. So here we have a subset of R, finite, the cardinality N, and we consider its subset, A plus A prime, N from A, and its product set, A times A prime, where A and A prime are from A. And of course, so we have n squared pairs here, A's of size n. And of course, we can choose A to be an arithmetic progression. And so we have here many repetitions. So the sum set is small. And we can also choose A to be a geometric progression so that the product set will be small. But is it possible to choose A in a special way such that the sum set and the product set both will be small? So Erdős and Semery conjectured that it's impossible. So they saw that one of them should be close to n squared. Well, maximum cardinality of A plus A and A would be fixed on constant and to 2 minus epsilon. They proved it should be more than linear. So they proved little omega of n, and people improved it over the years. And now the record is n to 4 over 3 plus and constant. I'm just mentioning it briefly just for to show the analogy. So this is the problem in the discrete setting, and in the Hausdorff-dimension setting, we have the this ring conjecture. And the question here is, does there exist subring, a Borel subring of the real numbers of Hausdorff-dimension strictly between 0 and 1? The dimension. Okay, and Edgar and Miller. So the answer is no. In 2002 or this, and also Bourgain gave an alternative proof using again some reduction of facts and tau. Going to tell a little bit more about it. Okay, so why is it related to the sum product? Why am I saying that it's a sum or related to sum product? So if we have such R, so of course it's a subring, so R plus R will be R. And R times R will be R. And if its dimension is strictly between 0 and 1, let's say it is alpha, so now we have a set of multi-dimension alpha, such that the sum is again dimension alpha and also the product. Contradicts this principle of the sum product. Okay, so you can view it as an analogy. And the question is really, do those settings really only look the same, but require different tools, or do they have anything in common? And if you look at the papers, for example, that improve the Erdős distinct distances problem, you see that the researchers that work on this problem are different from the researchers that prove the results in Falconer. So maybe it's just two different questions, just look similar. So in 2000, okay, so in 2000, Katz and Tau, in a paper, introduced a third setting that one can think of as something like an in-between setting, called the discretized setting, where they somehow showed some connection between the two settings. Okay, so let me just. So now I want to erase everything and tell you what is the discretized setting. If I'm telling about things that everyone is familiar with, just tell me so that I can.
Not yet.
No, okay. No, I mean Katz-Tau and discretized. Okay.
So you're not the person listening.
Okay, so.
Oh, for example, yeah.
Okay, I'm not sure.
I have to be a more. You are there.
Okay, so Katz-Tau discretized setting. We want to think of it as an in-between. So what are we looking at in this setting? So let's say that we have a set here, subset of let's say the unit Q. I think being RD. Usually D will be 2 or 1. And So now the sets that we're going to look at, so we had in one case, we had the finite subset, and in the other one, we had the infinite one, continuous one. So here we look at the unions of delta balls. So X is the union of delta balls, balls of radius there. Delta ball or delta cubes, hypercubes, included very much. And you can think of them as being interior disjoint, even only dyadic cubes. So take the union of such cubes, and what is the measure now? Instead of cardinality and dimension, we look at the covering number. The delta covering number of X is the minimal number of delta balls needed in order to cover X. So let's look at an example of a statement in this setting. So let's do it. Kind of an informal discussion. So discretize some product, that's fine. What kind of statement to expect here? So we will have a subset of R, and I will take of the interval 0, 1. And the set will be a union of delta intervals. So let's say that A is a union of a certain number of delta intervals. I will write it as delta to the minus alpha because this is going to correspond somehow to dimension alpha. That's just the number of. So union of delta to the minus alpha delta intervals. So this is the this is the interval 0, 1. Let's divide it into intervals. And you can think of delta as being 1 over n. You are more used to it. Okay, so two intervals of length 1 over n. And let's say that alpha is 1/2, just to be complete. So A is a subset of square root n intervals of length 1 over n. Yes. And subset of this. Okay, and now we can consider A plus A. And of course, by the continuity of the function, the sum, we don't really need to look at the sum of all these infinite points. We can just consider the middle point of those intervals that we took to our set A. Look at the sum set of the middle points of the intervals, and from this we can deduce what is A plus A. So it really is like a finite problem. We can look at A plus A and A times A. We know by the discrete version of the sum product, in the discrete setting, we know that if we consider only the middle points, the delta to the minus alpha middle points, we know that one of these sets will be large. So we know that either A plus A or A times A, let's say A plus A, has many, if we took the sum of the middle points here, we get many points over A plus A. But the question is now, so what can happen is that even though we have many points in the sum set, now when we try to cover them by delta intervals, so maybe there are many distinct points, but maybe they're very close to one another. So now when we try to cover them by delta intervals, we don't need too many delta intervals for the cover. Okay, so the new question will be, is it true? So maybe if the covering number of A is at least delta to the minus alpha or equals delta to the minus alpha, maybe it implies that either the covering number of A plus A or the covering number of A times A is at least something bigger than that, delta to the minus alpha minus C, or some positive C. Maybe it's true. And then the question is first of all, is it true? So is it true? And is it useful to anything? So is it true? So it's not true as it is stated. And there's a trivial counterexample where we can take all the points, all these, let's say that alpha is 1f, all the square root n intervals to be closest to 0 as we can. So if a, so as stated, a equals the interval 0, 1 over square root n is a counterexample. But if we add some additional assumption on this set A, so there is an additional non-concentration assumption. And then with this additional assumption, and I'm going to say it precisely in a second, with this, the statement is true. So with the additional assumptions, is it true? Yes, but this is the proof of the given. And is it useful? Yes. So Bourgain showed, so Katz and Tau said that they think that it will imply the ring conjecture, and Bourgain proved that this so this is right. So you can see that this is somewhat close to the discrete setting. So maybe tools from the discrete setting can help in order to prove statements like this. And it is useful, as Katz and Tau showed, to prove statements in the Hausdorff-dimension setting. So how is it? So let's say more formally, how is it useful, or why one can expect it to be useful to prove statements in the Hausdorff-dimension setting? So first, let's define this non-concentration more formally for definition. So if we have the subset of the unit Q in RD compact, of delta balls, and alpha is between 0 and 2, then we say that E delta alpha is there. This just means that we the delta alpha is the union of delta balls, and the non-concentration condition is that if we intersect our set with a ball over this R, then the volume is the usual effect measured in RD. The volume is at most delta to the power D times R divided by delta alpha. And here it's not my D minus some eta. Eta you should think of as something very small. It's like more natural to define this without the eta, and eta makes this condition even less strict. Allows more figure. How to interpret why do I call this non-concentration? What does this condition tell us? So wait, what's for R? 1 R is smaller than delta. Okay, all right. So how does it do that? So how to interpret this condition? So we know that. So in this example, we had square root n intervals of length 1 over n, right? So we took here square root n intervals. But what we want is that if we restrict to some sub-interval of length r, we want it to look more or less like the big set. What does it mean? So in the interval of length r, we can have how many potential intervals we can have. So we can have r over delta intervals of length delta. And if in the big set we took square root of them, the 1 over delta interval that we had. So here again, we want to have square root of them. We want this out. It just tells us that the number of, so if we restrict to an interval of length r, it looks more or less like the big set. Okay, so here, if the volume is at most this, so each ball of radius so now we try to cover it by balls of radius delta, and we divide, so how many balls of radius delta we will need in order to cover this intersection? Let's divide by the volume of each ball of radius delta, which is roughly, when there's this minus eta, which I'm ignoring now, this delta to the power of d, and this is the number of balls that we will need. This is the non-concentration condition. You can ask questions. Okay. Okay. So what Katz and Zahl showed, how did they connect it to the Hausdorff-dimension? So they showed that if we have such set of dimensions of Hausdorff-dimension plus alpha, then we can find so there exists a family of sets x delta for every dyadic delta. They actually showed something stronger. We don't need to go through all the dyadic. We showed that we could take delta to be hyperdyadic. But there exists such a collection for x delta such that for each delta, x delta is delta alpha. This there. And this family strongly cover. By strongly cover, I mean that each element of E is in infinitely many elements of this set. So each cover by infinitely. Covered by x delta for infinity. Yeah.
Can I ask a philosophical question?
Yeah.
Maybe there's no answer, but you raised it as a connection between the two, the discrete version and the continuous version. Maybe what I'm saying is completely wrong. I don't know, but so when I look at it, it looks to me, I recognize a lot of things from the continuous settings. The tools and objects you're using are very common in the continuous problems, right? But the discrete, when you say it's related to discrete, it's just because you have discrete points in some sense, but it's somehow the proof seems different than the proofs in the discrete case, or
So what do you mean? So I think, so I'm going to show that, and so the showing theorem that I introduced in the beginning, the thing that I'm now going to tell about is something that so we took the ideas from the discrete setting and use it here.
okay.
And also I think that in Borel is the Feynman's theorem about this. So I think that and also I just told you when we went earlier that in Pascal there are some ideas from the discrete of summary. So I think that really ideas from the discrete setting comes into play. I mean, of course, it's not there. I don't know, it's not that it is immediate. If you know the discrete setting, then this implies that this the text one, but you can see it in some of the works that ideas from the discrete setting show up. And the work that I'm now introducing is part of it.
It's a good answer, thank you.
Good question. Okay. So what is the connection that we show? So if we have a set of dimension at most alpha, it can be covered by such sets x delta that are delta alpha sets. And the other direction is even simpler. It will so more or less also the other direction. So you will need here. So this family x delta will need less restrictions around it. It doesn't have to be delta alpha set, only to be covered. So I don't want to say it precisely because I don't want to lose time. But so in some sense, you will need less requirements, but instead of alpha, you will need to have alpha minus epsilon, which is coming. more so, but kind of more or less the other directions too as well. Okay, so this is the lemma of Pascal. And in their paper, they formulated some conjectures in the discretized setting. They showed how they imply if one will prove them, or again later prove them, but if one proves them, they imply some of the statements in the Hausdorff-dimension setting. And yes, okay, I think this is any questions about it. Okay, so if not, then I want to tell you about another result in this work that with Josh Zahl, and I hope to tell you more about the proof, but I'm not sure that I will have time, so we will see. Okay, but one more result in the Hausdorff-dimension setting, then to tell you what is the discrete analog of this statement as I see it, and then maybe if we'll have time to tell you to sketch the proof. I want to start this day with the Hausdorff-dimension setting. And so before that it was on the right side of the row. So I'll try to keep the label the Hausdorff-dimension setting. Okay. So let me start by stating a theorem of finite. From I think 22, or maybe 21. And what he proves is that if we have the Borel set over 2, and it's Hausdorff-dimension alpha, we can look at this set, all the points in R2, we say in R2 and not necessarily in the set P, all those points such that the set of P distances to fix the point P, we look at all the distances between this point P and the set E, and we check the dimension of the set that we got. And if this dimension is very small, if it's smaller than alpha over 2, we take this set P to be an set. And Schmerz proved that this set of all such points P will have also dimension 0. Dimension of this set will be 0. So Bourgain has such a statement where instead of taking the in distances, it takes projection into a certain direction. And this can sometimes people refer to as a nonlinear projection. We take a two-dimensional set, we project it by fixing this P and taking this information. And so this is the analogy. Okay, so this is what Schmerz proved. And so by combining an example, example of Elekes and Falconer, one can show that so what happens to this set if instead of taking all the points where the dimension here is smaller than alpha over 2, let's try alpha over 2 plus a constant. Maybe still the set is going to be small. So there is an example of Elekes and Rónyai that shows that this is impossible. So alpha over 2 cannot replace alpha over 2 plus P for any constant. For any constant C. So for any C that you will determine confine, the set is such that this set of bad points will have positive dimension. Okay. Okay, now so what can still be said if we still want to change here alpha over 2 to alpha over 2 plus C, what can we still say? The theorem, and it's done with Josh Zahl. So what we prove is that same assumption, so E is a subset of R2, this dimension is alpha. And let's look at the set. So all the points. But so all the points of full dimension. So the field distances is increased alpha over 2 plus some constant C. So if C is sufficiently small, C. So now let's look at the set. So we cannot say that the set has dimension 0, but what we can say is that it has some special structure. So we show that K is flat. I need to prove what flat means. So roughly it means that it will have many thin triangles in finite position. So it's called curve. There are some constants with beta and C, and the probability measure so the support of this measure will be contained in K, supported on K, but that if we look at all the triples of points in K, such that the area of the triangle that they span, so how to write it? The area of the triangle that they span, so this is just the area. The volume in R2. If this area is less than R, then this is mu cube. The amount of such points will be at most constant times R to the beta. We bound the number of such group. Then this set will be curved, otherwise it is flat. Otherwise. Then so now, so this is the theorem. And what I wanted to say, so first of all, the question is, so we proved this, and we proved this using the reduction to the discretized setting. And now the question is like, what is the analog? What is the discretized statement that we want to prove? And then I wanted also to sketch a proof of maybe into school omission. Okay, so let me just tell you what is the discretized, or what is the discrete problem in the knowledge of this. Okay. Do you have any questions? I feel like maybe I'm running a little too fast.
Very clear.
Okay, great. Okay, so discrete setting. Here is a problem in the discrete setting, and then hopefully I will have enough time to convince you that this is the right analog in the sense that it helped us to prove it. You think about it as a analog. So the wait a minute. Now is the time when you can think and guess. Okay, so the problem that we look at here is the distinct distances from 3 points. So more or less the same as the other question, the question about distances, but this time we fix 3 points, P1, P2, and P3. And we have a set P subset over 2, finite of size n, divided to n. And we look only at distances that are spent between, so distances between these 3 points and the set P. We want to know how small this set of distances, so how small the distances between P1 and P, and the distances between P2 and P. You can think about the maximum between them or the union, it's the same thing. P3 and P. How small can that? Okay, so now we consider only 3 n pairs. We want to have many repetitions. So, okay. So why 3 points? Why not 2 points? So just that you have some feeling about this question. So let's say that each of these sets, the sets of distances, so now it's I already formulated the problem. Now I'm just discussing them. Okay, so this is not part of the formulation of the problem. So let's say that the cardinality of the set of distances between Pi and the set P, let's call it D. Okay, so if we have the distances between P1 and the set P, what does it mean? It means that I can draw D circles around P1, and these circles will have to support my set. The point of P will have to lie somewhere. But now let's say that I also have D distances between P2 and the same set P. This again means that I can, so now it means that I can draw D circles centered at the point P2, right? And they also support my set P. What does it mean? It means that my set P will have to lie in the intersection of these 2 families. So if I had D circles in each of the families, I have D squared points in the intersection of the families. And of course, I can take this to be my set P. So if my set P is of size n, I can have as few as square root of n still distances. But now what happens if I add a third point, P3, and I need to draw D circles around P3, and I still want to support more or less, it's going to support P, so I still want it to cover subset of size n from this point. Can I do that? So if instead of circles I add a straight line, that could do that. I can take D as vertical straight line, D or a horizontal straight line, and D straight line like this, and cover these squared points. But what happens for circles? So in general, the answer is no, I cannot cover these squared points unless the points P1, P2, P3 are polynomial. So the theorem says, so I guess it's the example where they are collinear is an example of Elekes, and this theorem about what happens if they are not collinear with the, so we guess Sharir and Shlomoshi. And the exponent will be of the result of Shlomoshi and Elekes is the example of the collinear case. So it says that if P1, P2, P3 not collinear, then the number of distinct, so for one, so for this I, for 1 and 3, such that this step we have at least some constant times n to 7 over 12. But more than square root. Okay. So this is the the statement in the discrete setting. And yeah, I'm not sure. So we started there. So how much time? So let me just say one thing about
I think another 10 minutes is fine.
sure.
Yeah,
Yeah. Okay, thanks.
I started late, so.
I'm
Yeah, okay.
I'm feeling in suspense, so I'm happy to.
Okay, great, thank you. Okay, that's good. Okay, so, okay, so this question, so how to start analyzing this question? So at first I studied the Elekes and Rónyai theorem, and it seemed like, I don't know if you believe me, but let's say that you believe me that we have it, and we also have the Hausdorff-dimension analogue. So I think this is more or less a special case. Why? So I have 3 points. It's all those circles. I have these 3 points that they fixed. And I have the set P of size n. And if someone will tell me that this, so let's take one point of this set P. And if someone will tell me the distance between P1 and this point, let's call it X, and the distance between P2 and this point, let's call it Y, I can, I know which point, so I don't need to know which point it was. Now, given X and Y, I can reproduce this point, and then I can compute the distance between this point to P3. Let's call it Z. So I have here some function Z, a function of X and Y. Right, so for each point of P, I can think of it as a pair X and Y, and given X and Y, I can compute Z. So I have this function, and if I had D distinct distances, so if this set will have D for each I, I'll write what I want. Okay, that's the intersection. Okay, so I want to look at the intersection of this function and the Cartesian product of D times D times D. So on the one hand, for each point of P, I have such triple X, Y, and Z that satisfy this quality, and also is here because I looked at all the distances between P1 and the set P, distances between P2 and the set P, distances between P3 and so for each point of P, I have a point here in the intersection. So I know that this intersection has cardinality with n side of P. On the other hand, if you believe me with the Elekes and Rónyai, this is kind of a variant of the Elekes and Rónyai theorem. And F will not be a polynomial, but this will be an algebraic surface. I can write it on this. And this is a version that's called Elekes and Rónyai. And we can bound the size of this intersection unless this surface is special, looks more or less like X plus Y plus C. So, so given that, we can have such bound in terms of the cardinality of D. So we have here cardinality of D, and with the recent improvements of Josh Zahl, the exponent will be 7. Okay, so this will give that the cardinality of D is at least n to the power 7. Okay, so now in the discrete setting, formulation. So what happens in the discrete setting is that we want to prove the same statement, and we know how to prove the statement about polynomial. Let's do that. But the thing is that if the points are very close, so they are not collinear. If they're collinear, we don't expect to have anything. But if the points are very close to be collinear, then maybe the distances will be very close to be the set of distances as 3 collinear points, the continuity. So if we only measure the delta covering number of the set of distances, so we can't tell really difference between 3 points that are almost collinear and 3 points that are actually collinear. So the set of distances will look as if those points were very collinear. And we won't be able to prove such a bound, right? But still, what we can do, so here, one thing we can do is just fix the 3 points and to assume the delta is between this one. So then we have to do the 3. So here 0 and 2, there is a constant. That's there, where the delta is small. And then, that for every triple of points, let's say this is the every triple of points in the unit square. And so I can write here non-collinear, but I'm going to say something stronger in a second, non-collinear. So if delta is sufficiently small, then no matter how close they are to be collinear, delta is sufficiently small, they will not be collinear anymore. And then we can expect to have a statement that we wanted. So if X is a subset of 1 squared, and it's the union of delta to the minus alpha delta Hausdorff, and it has the non-concentration condition for alpha squared, then the covering number of one of the distances will be more than delta to the minus alpha. So not the delta to the minus alpha minus 0. Okay, so this statement is true, but in the application, so this is, I guess, I'm sorry, but so, okay, so again, we had this statement. We understand that in order to prove it in the discrete setting, we need to fix the 3 points to take delta to be sufficiently small so that even in terms of this delta, we can see that the points are not linear, and then we can have the conclusion that we expected. So we have a set of delta to the minus alpha delta balls. They are not concentrated, then we expect that for some I, for I between 1 and 3, for one of these points, P1, P2, P3, there are many distinct distances. So we need much more delta ball in order to cover the certain distance. So this is true, but in the application, when we wanted to prove this theorem, we didn't really have this, we didn't really have, it wasn't the case that we fixed P1 to P3, and we could take delta to be as small as we wish. We had, for each delta, we had a family of triples that came together with this delta. Okay, so we couldn't fix the triple and then take delta to be small. So we needed to have here a statement which is a little bit more subtle. And what we showed is that if we have 3 points that span triangle of area is delta to the power of the C0, then we can still have this conclusion. So the area will depend on delta, but we showed how precisely it should depend on delta so that the conclusion will still hold. Okay, and then in order to prove this theorem, we show that if we have if this set is curved, we can find many triples such that the number of distributed span is small, right? But then by this theorem, they will have to span a triangle of very small area, and this will contradict the definition of curved set. Okay, I'll stop here. I hope to give more details about this. Okay, thanks for listening.